In this explainer, we're going to look at a scientific study on a new way to measure biological age. The approach uses small molecules in the blood, known as metabolites, to build what the researchers call a metabolomic aging clock.
So here's how we'll break it down. We'll start by looking at the concept of biological aging itself. Then we'll see how this new clock was built, what its key findings are, especially regarding health and mortality, and finally, what its potential future might look like. All right, to really understand the foundation of this research, we first need to distinguish between two fundamental concepts of what age actually means.
On one hand, you have chronological age. That's simple. It's the number of years you've been alive, and you can't change it. But on the other hand, there's biological age. This reflects the actual state of your body, the wear and tear at a molecular level. Unlike chronological age, this can vary a lot between people, and might even be something we can influence. This is why it's such a major focus in biomedical research.
Because of this variation, figuring out a reliable way to measure biological age has become a real priority. This has led scientists to develop tools known as biological aging clocks. The goal of these clocks is to give us a much more meaningful snapshot of a person's health than just their date of birth.
So, that brings us to the study we're examining today. The researchers set out to build a new kind of biological clock, and they decided to focus on a particular set of molecules, metabolites.
So, what are metabolites? Well, they're the small molecules left over from all the metabolic processes happening in your body, like turning food into energy. Think of them as a real-time snapshot of what's going on physiologically. Because their levels are known to predict the risk for various diseases and even mortality, they seemed like a very promising foundation for a new aging clock.
Now, to build a clock that's both robust and reliable, you need an enormous amount of data, and that's exactly what the researchers used. They drew on the UK Biobank, getting metabolic metadata from more than 225,000 middle-aged and older adults.
The process itself was quite rigorous. First, they measured the levels of 168 different metabolites in each person's blood plasma. Then, they took all that data and used it to train 17 different machine learning algorithms. The objective was to see which algorithm could get the best at predicting a person's actual chronological age, based only on their metabolite profile. So, after putting all those different models to the test, one came out on top. The result of this process was their new metabolic aging clock, which they decided to name mileage. The most important number that comes out of this clock is a metric they call the mileage delta. The concept is straightforward. It's simply the difference between the age the clock predicts for you and your actual chronological age. If that number is positive, it suggests your body is in a state of accelerated biological aging. And when they applied this to the entire study group, they found that for most people, about 68%, their metabolomic age was pretty close to their chronological age. But for about 32%, or nearly a third of the participants, there was a significant gap. Their biological age was more than 3.75 years older or younger than their birth certificate would suggest.
Okay, so they have this metric, the mileage delta. The next logical question is, does it actually correlate with anything meaningful in terms of health? That's what the researchers looked at next.
And the results were quite clear. The study's authors summarized it directly. A higher metabolic age consistently lined up with a whole range of negative health indicators.
If we look at the specific numbers, having a positive mileage delta was linked to things like higher frailty scores and shorter telomeres. It also corresponded to significantly higher odds of having a chronic illness, reporting poor health status, or just rating your own health as being worse. The clock also showed it could predict mortality. A high mileage delta translated to a 51% higher hazard of death from any cause. The statistical term for this is a hazard ratio of 1.51, which indicates a substantial increase in risk.
And you can see this clearly in the survival analysis. The group with a high mileage delta, those whose predicted biological age was significantly older than their real age, had a demonstrably lower probability of long-term survival.
These are significant findings, but to really understand their importance, it's helpful to see where they fit within the broader context of aging research.
This table provides a useful comparison with other known markers of aging. As you can see, the mileage delta was a stronger predictor of mortality risk than telomere length, for example. It wasn't quite as predictive as grip strength or the very comprehensive frailty index, but it clearly holds its own as a meaningful biomarker. Now, there was a key nuance in the findings. The clock proved to be very effective at identifying elevated risk. That is, a positive delta was strongly linked to poor health. However, the reverse was not as true. A negative delta, suggesting slower aging, had only a weak connection to better health outcomes. This suggests the clock's greatest strength is in flagging individuals who are at high risk.
So, what are the potential uses for a tool like this? They're quite broad. In a research setting, it could help evaluate interventions designed to slow aging. For clinical practice, it could serve as another biomarker to assess health risks, potentially helping to identify those risks before symptoms even appear. And for individuals, it offers a pretty intuitive, year-based way to think about personal health.
Ultimately, this line of research points towards a future where preventative medicine isn't just guided by the number of candles on a birthday cake. It raises the question of how things might change when we can rely on precise, dynamic measures of our own internal biology to guide our health.